Yeah, I'm Erlend. I work at Blank. I most of the time work as a developer, but I also do some security testing, I do some bug bounty hunting, I build some security tools, and I'm head of the OWASP chapter. And that's my Twitter handle up there as well. I was excited when we got the new OWASP Top 10 in 2017, because we got some new items in there. The blue ones are the ones that were new at the time. And we see the two green ones were merged into the new A5. And they were often confused with each other in the old A4 and A7. So they were just merged into one. But we see a couple of new things in there, and especially A4 and A8. And I said modern, but the thing is that modern kind of doesn't always mean modern. Because sometimes we tend to reinvent stuff when we create new frameworks. And we tend to reinvent bugs as well. So if we go to BugCrowd, which is one of the big bug bounty platforms, this is from their 2018 State of Bug Bounty report. We see that cross-site scripting is still one of the most common bugs we have. So we see we have stored cross-site scripting and reflected cross-site scripting as two of the most common ones. And we saw some great examples from Chris on server-side injection in the previous talk. If we go to HackerOne, which is another one of the big bug bounty platforms, we see a kind of a similar thing. We see cross-site scripting all the way to the top. This is from their hacker-powered security report. So we see cross-site scripting all the way to the top. We see that transportation, obviously, they have a big problem with cross-site scripting. And we see some of the injection vulnerabilities all the way to the bottom. Because in the OWASP Top 10, it says OWASP Top 10 A1 injection. It doesn't say SQL injection. So a lot of the types of bugs that are injection bugs are in that category. But let's move to the bugs themselves. I'm one of those people who likes to run demos, so I really liked Chris's talk. I really like when you can actually see what's going on. So I'm going to try to do the same thing. So the first thing I have here is a simple JSON XML API, sorry, where you can post a contact and you get an XML back. So we have the payload in this top corner here, or top box here, and we have the response in the lower box. So I can send in something, I get it back. So I can store something, fine. So our first bug is XML external entities. And this was now introduced in the OWASP Top 10, but it is actually quite an old bug. The oldest reference I could find to it is from 2002. One of the Norwegian security people called Sverre Huseby, he found one of these in Adobe Reader, I think it was in 2005. And then it kind of disappeared for a while, this bug. And now, the last years, it's come back in full bloom. So in this case, what we can do is we can inject and define our own entities within the XML itself. So what I'm doing here is I'm actually defining a new entity called content. And this content is going to be a system entity and is going to contain the contents of this file. So if I run this, I get the contents of the file down here. And it's this is Java, and in Java we can do easier things. We don't actually have to use file : /. We can just do dot, which means list the current files in the current folder. So there's an interesting file here called passwords.txt. Okay, what's in there? That's one of Chris's passwords, I think. Okay. So we can actually browse the file system. So we can't upload anything, we can't change anything, but we can read all the files that the current user running the application has access to. But this was XXE, but sometimes we have other types of functionality as well. Sometimes we use XSLT to transform an XML into, for instance, HTML. So in this case, we take this first thing that I posted. I posted a contact with a name and a last name and an email, and we can print that out as an HTML down here. Nothing really special about it. But XSLT has a lot of built-in functionality. So in this case, I'm changing the XSLT. So this would be a scenario where an attacker can upload an XSLT to create a representation of something. This actually happens. So in this case, I can figure out which kind of parser is being used in this case, which kind of XSLT is running here. So we can see the version number down there. And luckily, I see version 2.0, which is good for me because that has some cool functionality that I can abuse even more. But so the first thing we can do is we can use the document function, which is in XSLT version 1. In this case, we can include a valid XML into the XML that we're creating. So in this case, I'm just grabbing the POM XML, which is the Java deployment file, or that describes all the dependencies and everything. It's kind of the build manifest of this application. So we can see all the versions that's being used here and all kinds of stuff. But it is limited to only allowing you to include XML files. We could use XXC through XSLT. So we put, instead of attacking the XML like we did, the XSLT is also an XML document. So we could send the XSC in the XSLT instead. It would work just as fine. And then in the new version 2.0, which isn't new anymore, sorry, we have a new function called unparsed text, which allows us to include any file. So it doesn't have to be valid XML anymore. So in this case, we can once again include this file. This is often a limitation when we're doing XXC, that the end result has to be a valid XML, but when using this function, that's automatically handled for us, which is nice. We can also use this to try to load stuff off of other systems. So Chris mentioned this when you have attacked something and you're trying to pivot and attack other services that you can access. So in this case, we have something running on this IP that we see down here. So we can do kind of a port scan and we can figure out what's running there. So in this case, I found that, okay, this looks like Elasticsearch. So now I'm accessing something else through this server via an XSLT attack. What about blind XXC? That happens as well. And there are ways to get around that as well. What if I could upload an XXC, but I couldn't see the immediate result? So what you can do in that case is you can upload, you can do like a multi-stage thing where you tell it to go and download a DTD from your domain, and that domain grabs some files and puts them all together, and then you end up getting the result. So in this case, we tell it here to load this DTD from our evil hacker domain, and we see the DTD down here. So what it does is it defines an entity called xfill, where it tries to use some variable called data3 as a part of URI. And data3 is defined up here to contain the content of the shadow file. And then we just use all of these parameters down here, and voila, it just uploads the file if it can. So one of the reasons why I originally created this talk is because we saw a lot of these things being used in bug bounties, especially XXC has been used a lot. So this is from HackerOne, one of the bug reports for Twitter. What's one interesting thing here is it has medium severity, but quite a decent payout, I would say. 10,000. That's quite a nice sum of money for finding one bug. The next one, which was also recently added to the OWASP Top 10, is called insecure deserialization. And serialization is something we use in a lot of places. Like if we're serializing something, we're kind of converting something from, like, let's say, a Java object or a .NET object into something that we can store or transfer or send across a wire or something like that. So it could be XML, it could be JSON, it could be binary of some kind. And deserialization is the reverse. Once we receive this content, we try to convert it back into a Java object or a .NET object or something else, a PHP object. And this is used everywhere. So we're using this in all kinds of calls. We're using it in all kinds of REST and web service interfaces. We're using it in wire protocols and web services, caching, databases, et cetera, et cetera. So we're passing these objects back and forth. We're serializing and deserializing them and sending them back and forth. And in some of these places, we can do bad stuff. So things that we could do, we could have done denial of service. We could manipulate the state on the server, even completely compromise the server, which I am going to show. But before that, we need to talk about gadgets. So a gadget is basically an object that allows us to perform either the full attack or some stage of the attack. So on the top here, we have a normal API object. If I create that object based on an XML or a JSON, nothing bad is going to happen. It's going to create a simple object with a property called name, and no problem there. But then we have this utils class all the way to the bottom here, which is intended for us to just use internally. It's not intended to be a part of this API at all. But it allows us to just specify a file name, and it will run this thing. It's a bit of a construed example. But if I can get the API to try to deserialize an object into this object, it would immediately run the command given as file. How could this happen? Well, some of these JSON and XML frameworks, they allow us to specify the type. So you see here in this JSON, we have this type thing with a $. In front. And this is something we see in some of the frameworks. They allow us to specify this is the kind of type I intend for the rest of this stuff to be. And here we see the same thing for XML. We have this type attribute, and we specify the class. So in this case, you would have to know about the existence of this gadget, this runner class. But more often than that, we see that the attackers, they can use things that are built into the frameworks. There's dangerous functionality in the frameworks themselves. So here's one example from JSON and .NET. So in this case, we're using something called the object data provider. And then as a part of that, deserializing this, it creates a process which runs the calculator. So we can see here it says it runs the calculator. So it creates a process which takes in an array list of things, and it takes in the calculator. And then it invokes the method called start. So this is very handy if you want to attack something. This is taken from something called YSOSerial, which you can find on GitHub. But I mentioned demos, right? You don't want to see slides with code on it. You want to see demos. So in this case, I have my trusted context API. And Spring had this interesting bug where you could create dynamic proxies through the API. So in this case, I'm going to create a proxy for this original class called contact, but it's going to run this event process builder thing instead, and it's going to run a ping. Again, this attack is also taken from YSOSerial. So I'm going to just run this, and looks like it didn't work. Like class cast exception. That's a bummer. But that doesn't necessarily mean it didn't work. It just meant that once it had parsed this, because it actually created a Unix process down here, so it just means that it couldn't cast this thing afterwards. Okay, let's try something else then. So in this case, I'm going to build a function that calls bash. And in this case, it's going to do a reverse shell via bash. So it's going to create a connection to this IP that you see here, and to the port here. And we have to have something running there, of course. So we bring up a terminal on our trusted attacker server, and we start listening on that port. And then we try the attack. Okay. Do you see that? I got a new shell down here now. ID. Running as root. That's pretty bad. So now I actually hacked into the server using this. This is why insecure deserialization is super, super dangerous. I now have full control over this server, which in this case is a Docker container, because I was able to deserialize the wrong object. So back to HackerOne, we can find stuff like this as well. So this is from Starbucks. They had one of these bugs in their, I guess this is the Indian side. And they had a deserialization problem on JBoss MQ, which is rated a critical 9, which makes a lot of sense, if you ask me. Next one, server-side request forgery. So server-side request forgery is one of the very popular bugs that we've seen in the bug bounty space. A server-side request is basically something where, let's say a browser, it doesn't have to be a browser, some kind of a client can initiate a connection to our server and then make our server do another request to something else. So this could have been, let's say, an RSS reader. So you would send in, please give me the contents of this feed, and then our server application would go to that feed, bring it back in, and then show it to us. So we could say, please go to this URL and show me what's there. It could also be something as simple as a reverse proxy. So we're going to use that as an example for a bit. So let's say we have this URI here, and we have our server-side application acting as a reverse proxy. So this is a bit of pseudocode. What it tries to do is it tries to take the first part of the URI and remove that and replace it with images.example.org. So we're going to load the image from a different host, which is not accessible from the outside, and then show it back to the user. And it works perfectly given a benign request. But what happens if we go to this URL instead? Well, our trusted code is going to remove the first part and then add images.example.org, and then we end up with images.example.org.evil.com, which is a subdomain of evil.com, which we own. So we can now make it run requests towards our domain. And this can be useful. Let's say they were adding basic auth header or some other kind of authentication header to the requests that they send to their backend system. They will now send us those tokens instead of sending them to the intended server. There are other ways of doing this as well. In this case, where we can try to port scan the internal environment by creating a basic auth login at the beginning. So in this case, images.example.org would become the username, dummy would become the password, and the actual IP that we would go to would be 10.0.0.1. Some other examples. Let's say we have some kind of import functionality. So this could be the RSS feed, it could be some other thing. Let's say that this is intended functionality. The system is supposed to give us the possibility of going out and getting stuff. Let's say you can import your taxes or something like this. And so you can specify URL and it would go there and grab that stuff and bring it into the application. What happens if we start pointing it at internal resources? So we could point it at, in this case, a MongoDB, and maybe we could start exfilling data from an internal system instead, just like we did with the XSE previously. So the XSE actually acted as a server-side request forgery in one of the previous examples. Sometimes we can fool the parser as well. So we might have a friendly URI parser that would allow us to grab files as well. So in this case, we could grab the web config, which would contain possibly usernames and passwords for the application if this was a .NET application and it wasn't encrypted. And then we go to the cloud. And then we have this special IP, 169.254, 169.254, which is the metadata host. And this host contains a lot of information about the running node. And most specifically, it contains a path that you see at the center there called latest metadata IAM security credentials, which can allow us to get keys to log into the host, which can be pretty bad. Or we could, of course, use this as shown to access databases or other things that wasn't supposed to be available from the outside. Now you might think, okay, so this IP here, it's bad. We won't allow anyone to access this IP because we know that this IP is bad. But it turns out that our libraries, the libraries that we're using when parsing IPs, when parsing host names, etc., they're pretty friendly, a bit too friendly. So this is the original IP. This is the same IP, but with overflow. So then the libraries tend to think, oh, okay, I'm just going to do mod 256, and then, yeah, okay, so it's 169, okay. So here's a numeric IP. Here's a numeric IP with overflow. Here is a hex IP. Here's a hex IP without dots. Here's a hex IP without dots with overflow. Here's an octal IP. And here's an octal IP with overflow. So these are all the same IP. This is taken from the slides of a guy called Nicolas Grégoire, who has done a lot of research in this area. Okay, so we've successfully managed to block this evil IP. So we've taken out every case of these. So what happens if the attacker then creates a custom DNS entry that points to something that we're not supposed to be able to access? Well, we don't even have to do that because zip.io allows us to do that without creating our own domain. So if we do 127.001.zip.io, it resolves to the IP that we specified in the beginning. To obfuscate it a little bit, we could use base36. So again, it's the same IP, it just looks a bit different. And we can even add stuff in front. So www.bank.no and then this garbage. And it will still resolve to the same IP. And then, we forgot about a couple of things earlier because 0, 0, 0, 0. Ah, that's all the interfaces. 127 4 times. That's the same as 127.0.0.1. It's a full range. And IPv6. Oh, man. Okay, so an SSRF on HackerOne in this case was a company called Alien Vault, and they had a website called threatcrowd.org. And if we look all the way down to the bottom of this report, we find our trusted IP 169.254, 169.254. In this case, they actually have another endpoint, metadata.nicob.net, which is Nicolas Grégoire's domain, which can be used to get the IP. Next up is template injection. So we're using a lot of templates these days. We're using templates to create HTML typically from code. So we have some code with some variables in it, and we're trying to just insert stuff into this HTML. So we create a template, we run it through some kind of renderer, which replaces all these things with the contents of the variables. A lot of these things work something like this. So they kind of split it up, and then they eval the stuff that's in there, and then they kind of just concatenate these strings together. And it's supposed to be safe because we're not supposed to allow the attackers or the clients to specify the templates. Like the templates is something that we as developers create when we create the application. It's not something that someone externally is going to provide for us. But sometimes bad stuff happens. So we have an example here. Let's say we have title equals hello, and then we render some template with title in it, and the end result is hello with H1 around. But then we have this scenario. So we were trying to avoid duplication. So we are creating these kind of modules, and then we're putting one module into another. And it kind of works. We just test it, and it works. Like so, if title is hello and body is world, the first render is going to render a H1 hello, and then we put that into the second template, and we render it there, and then what we get out is something looking like this. But what happens if the title contains a template? So it's provided by the end user in this case. So if the title contains a template, let's say 2 by 2 in curly braces, it's going to get rendered in the second stage because we're going to double evaluate the first template. So we put it in as title, and then we render that, and out comes a new template. And then we put that template into another template, and out comes the number 4 instead. This is pretty bad because now we actually can run code in there. We ran 2 by 2, which is not very interesting, but it's a way that we use to prove that template injection exists, much like alert in a cross-site scripting. So here's an example of an app. In this case, the upper screen, part of the screen here, is the rendered HTML, and the bottom of the screen is the HTML source that's returned from the server. So these two things here, they show the same thing. This one renders it, this one just shows the source. So I had a URL parameter with my name in it. It rendered hello and put my name in there. It's here, and you can see it rendered here. Nothing special about that. So let's, instead of my name, let's put 2 by 3. That says hello 6. And we can even see that the 6 is coming back from the server. So in this case, we have a pretty clear indication that we have double evaluation of templates on the server. What can we do with that? Well, we can start to poke around and try to figure out what framework this is. In this case, it's a framework called Twig, which is a PHP framework. And so if I just do _self, we see could not be converted to a string, and we see like Twig environment PHP, et cetera, evaled code. So obviously something was running, which is nice if we're the attacker. So in Twig, there was a way to run arbitrary code. We could register a filter callback. In this case, we called it exec. And then we could create a filter and call it, for instance, ID, which would run the ID function in Linux. So we see that in this case, the application is running as --data. But again, running code, it's kind of boring. We want access to the server instead. So what we're going to do in this case is we're going to do the exact same thing as we did earlier. We're going to run a reverse bash shell, bring up our trusted, oh, we're still logged in, nice, did the old one. Set up a new listener and attack this instead. So now you can see it says, down here it says data, because we're now logged in as that user. And we're on this separate host. And if we run ID, we see the same thing that we saw earlier, that we are data user. Which is, again, fairly dangerous. So this was the server-side thing. But we can have a mix of templates on the server and the client side. So in this case, we saw it said 6 up here, and it said 6 down here. And what we sent in was 2 times 3. So what happens if, in this case, well, we get 2 times 3 back from the server, but it says 6 up here. Okay. Well, it's because, in this case, this is wrapped in ng app, and we have Angular running here. So in this case, we mixed a server-side template with a client-side template, and we ended up injecting a template server-side into something that is then invoked as a template client-side. This is something that I found quite a couple of times, actually, when doing bug bounty hunting. So, okay, we try the obvious thing. We want to run alert. Okay, that didn't work. Because in this version of Angular, which is quite old, they had a sandbox. And this sandbox was supposed to stop certain JavaScript functions from working, so to protect the developers. But of course, someone quickly found a bypass. It's going to pop up 2 times for some reason. So what we're doing in this case is we create a string, and then we access the constructor of the string, which is the string constructor. And then we access the constructor of the string constructor, which is the function constructor. And then we invoke the function constructor with alert1, and then we call that function. So we escape the sandbox by jumping through constructors. This is a common way to exploit JavaScript frameworks. They patched this vulnerability, but the people who found this vulnerability, they found a new one, and a new one, and a new one. And now in the latest version of Angular 1, there is no sandbox. They decided just to remove it altogether because it was really hard to get it right. And they had in their documentation, don't mix server-side and client-side templating. It's been in the Angular documentation forever, or as long as I could find. And it was there clearly, but people didn't read it. But as a general thing, don't double evaluate templates. So don't mix server-side and client-side templates, and don't double evaluate templates. The next thing we're going to touch briefly on is CORS, because we've seen that a lot in bug bounties as well. So we saw these headers popping up quite a few years ago. Access control allow origin. And it's sometimes hard to understand what it actually means, because this one is pretty simple, but then we have all the other headers as well. And so I plugged it into Google Translate, and I told it to translate from HTTP to English. And so access control allow origin example.com, access control allow credentials true. In English would be, if the user is logged in and visits example.com, please allow that site to access the user's data. Okay, yeah, makes sense. Okay, so what if I do access control allow origin star, access control allow credentials true. If the user is logged in, please allow any site the user visits to access the user's data. Haha, but the browsers were smarter than us because they knew that we would do this mistake. So they said, okay, so access control allow origin star is not allowed. So the browsers will not honor this. But then people figured out, I wish this was possible anyway. So they came up with the echo. What they will do is they will grab the origin header on the incoming request, and then they will echo it back as the access control allow origin header. So they reinvent the asterisk or the star, but this time it works because now it can no longer we can no longer filter it as a browser. A lot of this research is done by a person called James Kettle, who works at Portswigger, which creates Burp Suite, which Chris showed in his previous talk. Another common mistake is insufficient validation. So if the origin ends with something, so it should end with example.com because it's our origin. Great, so we're going to add this header as long as the origin ends with example.com, like not example.com. Again, this is an example from James Kettle. And then we have an interesting thing, something called the null origin. Access control allow origin null. Access control allow credentials true. What does that even mean? What does null mean in this case? Let's ask Google Translate again, because it knows everything apparently. Access control allow origin null. Access control allow credentials true. If the user is logged in, please allow any site the user visits to access the user's data as long as the site knows how to use an iframe with the sandbox attribute. Okay. Looks like this. We create an iframe with the sandbox that says allow scripts, allow forms, and then we do the XHTTP request inside there. Then we get the null origin, and then it works again. Okay, that's a shame. Back to HackerOne and back to James Kettle. This is actually the exact example. I showed it with example. In this case, if you see down here, Zomato allowed notzomato.com. Nice. All right, next one, subdomain takeover. This one I'm not going to demo. I didn't demo the previous one either, but I'm not going to demo this one. I'm going to demo the last one. A guy called Frans Rosen from Detectify in Sweden, he did a lot of research in this space back in 2014. And this is kind of an exploit of how we configure DNS. We see a lot of these cloud services, they allow us to specify, to kind of get our name as a part of their subdomain. So Heroku, in this case, we can create an application with a given name, and that would be a part of the subdomain for that app. And then we see the same thing for things like AWS and lots of other services. They have the same thing. But as the owner of a domain, we don't really want to point at something .herokuapp.com or something .github.io. We want our domain name to be there. So of course what we do is we create an application, in this case OWASP.herokuapp.com, and then we configure this application to have a custom domain name. So it could be owasp.example.com if we are the owners of the example.com domain. And then we create a CNAME entry in our DNS, which points to Heroku's DNS. So we say, if you want to resolve owasp.example.com, please go over to Heroku DNS to resolve it. And I think Heroku is working on this now, so it shouldn't be possible anymore, but I'm not sure how far they've gotten in with this. But let's see what that would look like. So we do an NS lookup of this IP, or this hostname, sorry, and we ask the registrar, and what we get back is, okay, yeah, there's an entry here. Please go ask this other thing and get the IP from there. Let's look at it in a different way. So we want to look up this IP, OWASP.hackable network. We go to DNS1.hackable network. What's the IP? You should go see this other thing. So we go over there. We ask, do you have an IP for this thing? We get an IP back, and then we can access the intended service. And this works just as intended. There's nothing wrong here right now. The problem is maybe this little application that we created over at Heroku was something we didn't intend to keep. So we used it for some time, and then we removed it. We went in and we deleted it. But we forgot to update the DNS. So the attacker can now go in and create a new application with the same name. And they will now own our subdomain. This is pretty useful for phishing, because you now have a proper domain for the target. We can use this to steal or inject cookies. We can use this to put in all kinds of material that the company doesn't want to be affiliated with. And we can even use it to create rogue HTTPS certificates. So here's an example from Shopify on HackerOne, where they had a subdomain takeover. And here's another fun little gem. Simon Grushki has hacked produber.com. This is from the certificate transparency log. So the CAs, every certificate that they issue has to be published in the certificate transparency log. In this case, a guy was able to as a part of the bug bounty, was able to take over prod2.uber.com and then created a certificate with his name has hacked prod2uber.com. And it stays there forever because this is a log that's not supposed to be changed. Last thing I'm going to talk about is web cache poisoning. Again, we're heading over to James Kettle of Portswigger. He was trying to figure out how to exploit unexploitable bugs, and he's published a lot of great material around this, and even some plugins for Burp Suite. So let's look at what web cache poisoning means. So we have a cache, we have a server, and we have a client. So the client is intending to go to the server and hits the cache that's sitting in front of this, because we want to protect our server from a lot of traffic. So we put up a cache. So the client, there's a miss in the cache, so it looks up the actual resource from the server, returns it, and puts it in the cache, and then returns the result back to the client. So the next client that comes in, or it could be the same client, will then hit, when it tries to access the same resource, because there's now an entry in the cache, and we'll get the cached entry. And this is fine. This is exactly how caching is supposed to work. But what happens if our attacker is in there, and the attacker is trying to exploit an unexploitable bug? So the attacker knows that there is a bug on the server, and the attacker tries to attack the clients, not the server itself. So this could be a cross-site scripting, for instance. A reflected cross-site scripting that's hard to exploit. So in this case, the attacker could send something malicious to the server, make the server render this in a bad way, and then store that result in the cache. So the next thing that happens is one of the benign client comes in and wants to access the same resource, and now gets the poisoned entry instead. And then the attacker has now attacked this client. So an example of this. So we have this nice little thing here. So we have, up here we have the request headers. So this is the stuff that we're sending. And down here we're going to see the response. So in this case we see, okay, we got a 200 okay, and we got this script tag with the domain name in it. Then we have the attacker. And the attacker has figured out that if I add an extra header called x-forwarded hosts and puts attacker.com in there, that's going to overwrite the other one. So in this case, we see now, instead of saying www.attacker.com, it now says web.hackablenetwork.com, it now says attacker.com. But this is not exactly what we want, because if we go back to the client here, the client still sees hackablenetwork.com, and we want to attack the client. So we're going to load. I intentionally added a URL parameter while poisoning this just to try it out. So we're not going to try to poison whatever the client's seeing. So now see, I sent with this thing, but it still says www.hackablenetwork.com down here. So I'm just going to have to try, because I need to find the time where the cache expires, and at that time I should be able to poison the cache. So I need just to send this a couple of times, and it actually tells me here that it's valid for 30 seconds, and now you see it changed to attacker.com down here. And if we go back to the benign client, which is not sending this extra header, it now says attacker.com. So, what if we try this with the audience? Woohoo! If you could bring up your phone and go to this nice little website here. I'm not going to hack you. It should look something like this. It's not dangerous. No worries. So in this case, all I'm doing, I've loaded this site, and it shows the OWASP logo, or the OWASP Norway Day logo. What I'm going to do now, can you see this logo on your phones? Yep, okay, good. What I'm now going to try to do is poison it. So all I'm doing is just sending a lot of requests to the server with this extra header tied to it. So I'm just sending, as a success. Can you now reload the page on your phone? It should look something like this. So all I did was actually to send a request with this extra header, and I was able to change what was cached, because there was a bug in the application, but it would be really hard for me to get a client to send this header. So I can poison the cache myself and then make you reload the poisoned version. So what James found was that there were quite a few headers that were interested in this respect. So there was x-host, x-forwarded host, x-original URL, x-rewrite URL. So these were at least some of the ones that were interesting. And so you can make it cache something on a different URL, for instance, with some of these headers. It's quite weird. But the thing is, we don't necessarily, as developers, know if we're using these headers. It might be that the framework supports them, and we don't know. So this isn't necessarily that easy to attack, because we need to figure out which URL parameters are used in the cache keys in this cache that sits up front. Are user agents used? Maybe then if we try to poison it as Chrome and the client we try to attack is using Firefox, they won't be attacked. So we need to figure that out as well. But there is a tool, as mentioned. James Kettle created this thing called ParaMiner, which is a burp suite extension that you can use to figure out what is used as a part of the cache key. To stop this, we can, of course, block these headers while they're coming in. So we don't want these headers. We don't want to trust them when they're coming from the outside. We don't want anyone on the outside to be able to say X host and X forwarded host. That's stuff that's meant to be used in our infrastructure, not from the outside. We can add these headers to the cache key as well. So then it would only be get a cache hit if you also sent the attacking header, which means you were the attacker. So that would also work. We should, of course, sanitize stuff. So there was a bug in the application in this case as well. And we can use this ParaMiner extension as an audit mechanism as well. So here are some resources for what I just spoke about. So we have disclosed H1, the Twitter account that's, I should say twitter.com, not just Twitter, sorry. That's a Twitter account that puts out all these HackerOne reports that allow disclosure. So you can, like all the reports that I showed you pictures of, they are where the company and the bug bounty hunter have agreed that they should publish this for everyone to see. And this is one of the ways that I'm learning a lot these days. Just reading these reports is super interesting. The second link is Hacktivity on HackerOne. That's the same thing, really. It just shows all the reports. I showed you some insecure deserialization. That's from WISO serial that you can see there. XSLT, James Kettle. Server-side template injection, also James Kettle. Hostile subdomain takeover from Detectify. Yeah, course stuff by James Kettle and practical web cache poisoning by, again, James Kettle. So he's done a lot of great research, James Kettle, in the last days. So he's also someone you should follow the stuff that he does. He does amazing stuff. The application that I used for insecure deserialization and XXE attack is available on GitHub. So you can download it and run it as a Docker container if you want to try it out yourself. It's there. Thank you. Any questions? No. Okay, then we'll have a 15-minute break and then start back up again. Thanks. Oh, sorry. Yeah.
So, with the board of OWASP Norway, just want to say thank you to Erlend for being a leader of OWASP Norway for 7 years. And has been a driving force in the Norwegian security community for at least 10 years, and also outside of Norway, like we were in Australia a couple of months ago, having a talk. So yeah, so I would say thank you for spreading knowledge about security around the world.
Thank you.
So,